Okay, so picking up from the last time, what we had was a set of IID, that stands for identically and independently distributed random variables. And we defined this variable mn, which was the average of these random variables. Okay, what I showed last time was that the expected value of the mean was mu, which was the underlying mean of these variables, and that the variance was 1 over n times sigma squared. Okay, so why is this an exciting result? It's exciting because as n goes to infinity, the variance of this mean gets smaller and smaller, right? So this is useful for measuring the mean or estimating the mean from a bunch of actual measurements, right? But one important question is kind of how fast does my estimate get to the mean, right? So in the limit, things go to 0, but I want to know a bound on, for example, how many random variable instances do I need to have to get a sufficiently good estimate of the mean? So we can answer that question using Chebyshev's inequality. So how fast do we get there? So remember Chebyshev's inequality. Let me write it down again. I guess I used Ness. Chebyshev's inequality. What was that? That said that the probability that x minus its expected value was greater than or equal to epsilon was less than or equal to 1 over epsilon squared times the variance of x. Okay, so this is something that we said, okay, if all I knew was the mean and the variance of a random variable, I could still get some useful information about how close an expected measurement is from the truth, right? So here, what is my situation? My x is going to be the mean of a bunch of random variables. My expected value of x is going to be mu, and my variance of x is going to be 1 over n sigma squared. So plugging that all in, that's like saying the probability that the mean of a bunch of random variables is further away from mu than epsilon is less than or equal to 1 over epsilon squared times 1 over n sigma squared. Okay, this kind of tells me how fast do I converge to the mean, right? Or I could flip this around if I wanted to, and I could say, okay, the probability that I am within epsilon of the mean is greater than or equal to 1 minus 1 over n epsilon squared sigma squared. Basically, these are the same thing, okay? And so now I can do like a word problem. You see these kinds of things at this point in probability courses. I could say, okay, let's suppose that I had a bunch of random variables and the variance of each of them, IID, was equal to 5, right? That's my sigma squared. Now I want to know how big does n have to be so that I am 99% sure of being within, say, 0.01 of the actual true mean. Okay, so now I kind of look back at my, my Chebyshev, and I say, okay, this is the thing I wrote before, and I have to think about how do I map this on to stuff that I have been told, right? So I don't know n. This is what I need to figure out. I do know epsilon. My epsilon is 0.01. And I guess actually I would be using the opposite version of this. Let me just kind of say this a different way. So the version that I want to use would be this. Right? So my epsilon is 0.01. My sigma squared I have from up here is 5, right? So now I can start moving stuff around, and I can say, okay, that's like saying the probability that I am within 0.01 is going to be 1 over 1 minus n times 0.01 squared times 5. And I want this number to be at least 0.99, right? I want to be 99% sure. So now I can work out my word problem, and I can say, okay, well, that means that my 1 over n times 1 over 10,000, and I have a 5 in the top, should be less than or equal to 0.01, and that means that I have basically 50,000 over n should be less than or equal to 0.01. Flipping stuff around, that's like saying that I add 2 zeros, and I should have n to be at least 5 million. Okay, so I need to be, I need to take 5 million samples to be 99% sure that I'm within 0.01 of the mean, right? So this kind of thing is a typical kind of calculation. Now this idea leads to a really important result, and that's called the law. Well, there are these laws of large numbers, and in particular, the one I want to talk about is called the weak law of large numbers. And sometimes you'll see this abbreviated as WLLN. Okay. All this says, and if I look at, if I look at my Chebyshev, all it says basically is that take n going to infinity in one of these expressions. It says that the limit, as n goes to infinity, of the probability that the mean is within epsilon of the truth is equal to 1. Okay? That is, if I tell you epsilon, we can take n large enough that mn is arbitrarily close to that, right? With basically 1 probability. So that's like saying, suppose I have a coin that is biased, and I keep on flipping it, right? So, let's suppose I have a biased coin. That's like saying, how would I estimate the bias of the coin? Well, I could keep on flipping the coin, and I could count the number of heads, and I could divide that through by the number of flips that I took. That's the sample mean. And so it's like saying the probability that, if I were to take the total number of flips over the total number of successes, and I asked how close is that going to get to the underlying p, which is like the p of the Bernoulli random variable, well, for any epsilon I choose in the limit, that's going to basically get very, very close to p. Okay, so we already know that the Chebyshev bound is conservative, so actually we may get to the truth a lot faster than Chebyshev would predict. Okay, and there's also something called the strong law of large numbers, and the difference is a little subtle. That one says that the probability that in the limit the mean equals mu is equal to 1. Okay? This is a little bit subtle. What this is saying is that for any sequence, right, in the limit, the average of that sequence is going to converge to the right mean. A different way of saying this is that you can't get some sort of an oddball sequence that in the limit as n goes to infinity doesn't do the right thing. Like, I can't, by some miracle get some weirdo sequence of coin flips that doesn't doesn't in the limit converge to the mean, right? I can't keep on spinning the roulette wheel and have the ratio of red and blacks converge to the true ratio of red and blacks in the limit, right? So this notion of kind of statistical regularity is really important, and as you get closer to higher level work in probability, like if you're a graduate student taking a course in stochastic signals and systems, you'll deal more with these kinds of limiting type behaviors of collections of random variables. And this is also kind of like the underlying gambler's fallacy that says, oh, well, I know that in the limit everything will balance out. Well, that's true. Like if you get, if you've got a fair coin and you get 50 tail flips in a row, it's true that in the long-term average, those oddball sequence of 50 coin flips in tails will balance out. The fallacy part is that it may take you an infinitely long time for that balancing out to occur. And so your money may have run out by the time your law of averages works in your favor. There's nothing that says that in the near-term horizon that balancing out has to happen at any given rate. So, okay, so hopefully that's kind of interesting, and we'll talk more about sums of random variables in the next lesson.